I'll be drawing both a system diagram and a free body diagram for this. So here's a 30-degree ramp. There's the block being pushed. The displacement, I'll start the block down here actually. The displacement is 3 meters along the hypotenuse of the ramp. Okay, so this arrow I'm drawing here, that's the displacement. That's 3.0 meters. It's parallel to the ramp. Now, in terms of the free body diagram, I'll draw my box and the forces. So we'll have gravity straight down. Which I'll be resolving into components. We have friction. So since the box is being pushed up a ramp, and it is moving up a ramp, the coefficient of the friction will be the opposite way. So friction will be down the ramp. And this is going at a constant velocity, so the applied force has to be long enough to balance out those two downward forces, the friction and FGX. Finally, we'll have a normal force, which is going to be balanced with FGY. This is very typical of a lot of ramp problems we've done. Work is going to equal to, in general, force times displacement times cosine of theta. So for each of these forces I'm asked to do, I should find the value of those forces. So that's a dynamics problem for now. So maybe I'll do that first. Let's figure out the value of all four of those forces. So not much is given here. I think one force I can find out is Fg. Fg equals to mg. So that's 20 kilograms times 9.8. That'll be 196 newtons. Okay, so I know that the force of gravity is 196 newtons. I'll also label these angles here. Forgot about that. It's a 30-degree ramp. So in my free body diagram, my 30 degrees goes in that small triangle there. A little hard to see. Okay, the normal force. I know that the normal force has to be balanced with Fgy. Okay, so I'm going to work a bit on the normal force. F normal will equal to Fgy. And that is the one component of gravity. So using trig ratios, it is equal to mg cosine of the angle. All right, so that's the normal force. I can get the value of that. It won't end up mattering too much, but I'll get its value. Okay, the mass is 20. G is 9.8, and times cosine of 30 degrees. So basically 196 times cosine of 30 degrees. Let me calculate that. Make sure the calculator is in degrees mode. Okay, I'm getting 169.74 newtons, which I'll underline 2 sig figs. Okay, that's the magnitude of the normal force, which is useful. So I'll just call this, which is useful to find the frictional force. Frictional force is mu times normal. So that'll be 0.60 is the coefficient of friction times the normal I just got, which I have not yet cleared from my calculator screen. So that's useful. I can just continue on and hit times 0.60 on my calculator. So getting 101.84. And I'm going to try to find my applied force as well. So based on the free body diagram, my applied force, which is pushing up the ramp, must balance out both friction as well as FGX added together. So these two that are added together, they're both pointing down the ramp. They want to make the box go down the ramp. So applied force has to perfectly balance them to keep this thing at a constant velocity. Okay, so that's going to be give myself some more room here. Friction, which I just got, plus the x component of gravity would be mg sine of theta. So now the values will be the 101.84 for friction, plus I have to do this mg sine theta thing. Well, sine of 30 is a half. A half times 20 is just 10, and 10 times 9.8 is 98. So actually it's not so bad. Plus 98. That'll give 199.84 newtons. Okay, so I actually have the magnitudes of all the forces, actually. All four of them. Okay, so let's start calculating the works now. The question wants us to do works. So A, the work done by the applied force. Okay, so work done by the applied force will equal the applied force times the displacement times cosine of 0 degrees. The applied force and the displacement are pointing in the exact same direction, so the angle is 0 degrees. So that will be, I'll take the applied force I just calculated, 199.84 to 2 sig figs, times the displacement is given as 3.0. Put on the calculator, I'm getting 600 basically, or to 2 sig figs, 6.0 times 10 squared joules. B, the work done by friction, WF, would be the force of friction times the displacement times cosine. The angle here would be 180 degrees. Friction is in the exact opposite direction of the displacement. So subbing in numbers, that'll be 101.84 multiplied by the displacement of 3, and cosine of 180 is -1. Okay, calculate that. Giving me -305, so -3.1 times 10 squared joules. Okay, C, gravity. Work done by gravity will be the force of gravity times the displacement times cosine of, okay, theta is trickier for this one. I'm going to highlight in blue here to match my blue writing. The force of gravity is actually straight down. The displacement is upwards at 30 degrees. So those two arrows, if I were to draw those two arrows tail to tail, so there's gravity, there's displacement, what would be the angle between them? Well, I would do 90 plus 30. Okay, I would do a right angle of 90. There's 90 plus the 30 that the displacement is pointing in. So that'll make the angle 120 degrees. So theta is going to be 120 degrees. Okay, so the values, the force of gravity, I got 196 newtons from before. Displacement's 3, and my angle is 120 degrees. So the cosine of 120 degrees, that is one of the special angles. If you follow the cast rule as well, you'll realize that it's a negative number. It's equal to negative negative a half, I believe. Let me just double check this in the calculator. Yeah, so cosine 120 is a special angle equals to negative a half. So I multiply that all together. 196 times 3 times negative a half gives me negative 294. So negative 2.9 times 10 squared joules. And finally, the work done by the normal force. I'm just going to write the answer. It's going to be 0. It's going to be 0 because the angle is 90 degrees, the normal force versus the displacement. Cosine of 90 degrees is equal to 0. Those are my 4 works. You may notice that if I add them all together, they will actually add up to 0, which makes sense because this is going at a constant velocity. So it's not speeding up, not slowing down, so there should be no change of kinetic energy. And that means that the net work should be 0.